Okay, so many times in robotics, we are not interested in the forward problem, but we are interested in the reverse problem, which is if I told you there was a function y equals f of x, okay? So given x, find y. This is the forward problem. Okay, and that's typically very easy. You just plug in the value of x and you get y. However, we are interested in the reverse problem, which is given y, find x. Okay, and many times you cannot just find the value for x, because f of x can be any complex quantity. It could have exponential, it could have sines, cosine in some weird combination. So example would be, okay, I'll give a simple example which you can probably solve analytically, but we'll sort of use this to build a numerical code and then use that to do inverse kinematics. So let's say that f of x is x squared minus x minus 2, a simple quadratic equation. If I were to ask you solve for, so find x such that y equals 0, then you can probably do this in your head. The solving a quadratic equation, there's a formula for doing that. And that formula, if you use that, you'll see that it gives you solution. It'll give you x equals -1 and x equals 2. So if it's a quadratic equation, then you'll have two roots. And the way to check this is if you put f equals -1, then you'll see that it actually comes out to be 0. And again, if you put x equals 2, then you'll get 0. That means that this equation is satisfied for these two values, and those are the roots of the equation. Okay. Another way of doing this is to actually make a plot. So if you make a plot of y or f of x against x, then you should get something which looks like this. And these intercepts on the x-axis are actually -1 and 2. Okay. So you can use this to sort of eyeball the roots, and then once you know where the roots lie, you can then put that in the program. So what I'm going to do is I'm going to introduce you to a function called fsolve, which is used to find the inverse, solve for the inverse problem. So that is kind of important to solve root finding problems, as we'll see. Okay, so the next thing we do is we'll write code which will produce the same solution for y equals f of x equals 0, but will not use the formula, quadratic formula, but instead we'll use fsolve. Okay, so that's Matlab. Okay, same thing, CLC, close all, clear all. And now let me, first what I'll do is I'll actually draw the plot of f of x versus x to show you that the roots are between -1 and 2. And once I do that, I'll use fsolve to find the exact root. So let's try to generate first points on the x-axis from -6 to 6. Okay, and this can be changed anytime because it's just code, this one line of code. So for I equals 1 to length of x, I need to find, I need this. Let me just write it as y equals x square minus x minus 2. Okay. And then I do plot x versus y, and let's save the red. Okay, so when I run this, you can see that, okay, it's really hard to see. 0 is right here. And so the roots are somewhere in there. If you want to make a better plot, what you can do is you can put grid on, or you can, if you want to do it without running the program, you can just say grid on, and then open the figure. And so you can see now the grid. Now it's easier to see the roots. You can eyeball the root. It's somewhere between -2 and 0. That's actually -1. And then the other root is exactly at 2. If you want, you can put your cursor and then use the left and right arrow to move it. Or you can also move it with the cursor like this. One second, let me just change the, I think my font is too small for you to see. Let me increase the font. So if you want to increase the font, it's slightly different for Windows, but you want to somehow hit the preferences and go to fonts. And let me change that to 15. Apply. Okay, slightly bigger. Okay, so now we know the root lies between -6 and 6 somewhere. Let's see how to use fsolve. Okay, so if I tell you a new command, the first thing you want to do is type help fsolve, and that gives you more information about the command. Okay, let's build up from this. So it says x equals fsolve fun x0 starts the matrix at x0 and tries to solve the equation in fun. So that would be your y equals f of x, and returns the matrix equation values f evaluated at x. Okay, and then it gets a little bit fancier. You can put options. So that's just basically the extra argument. It explains the extra argument. And there's another way to define it. I would say don't complicate your life. Just try to keep it simple. What I like to do sometimes is just see what's the simple example they've solved and copy paste that and then modify it. So let's see, here looks like there are a couple of examples here. This is one of them. Okay, here is another one. So let's use this one because this one uses what is known as anonymous functions. If you want, you do it this way. But since some people find this confusing, so I'm just going to use this function. So let me copy this, paste it here, and then copy that, paste it here. And note that this is not solving the problem at hand. This is basically solving a different problem. It's actually finding the roots of sine of x. Now, when I run this, it'll actually not work. So if I run this, the issue with this code is that, and this is something which I've not quite talked in the first class, is that if you have a script, which is a script, and then if you have a function on the way, then it will not work because you can't mix the script and a function in the way I've shown. The only way you can mix a script and function is to have all functions in the file. So one way of doing this is to make this external. So you can cut this, make a new file, and this is what I've done in my introduction class. Save this, and it asks for my fun. So, and run this, or you can actually call this function example roots and do it that way. Let me show you both ways. Let me just run this first. Okay, so this is not, as I said, not related to the quadratic equation, but I think it's important for you to get a feel of how to use the help. So here, this is solving a different problem. This is the solution. Okay, there are 3 values. This was one way of executing the file as a separate file, but if you want to make it a part of the first file, then what you can do is you can put this here and call this function example roots. Always note that the name of the function should be the same as the name of the file. Okay. Okay. What are the benefits of fsolve over roots? Okay, let's see if there's a function called root. I did not know there was a function called root. So help roots computes the roots of the polynomial whose coefficient are the elements of the vector C. So the way the roots stand, it looks to me that roots can only solve if it's a polynomial equation. So yes, for x square minus x minus 2, you can use roots and it will give you the same answer. But if you have a non-linear function, say exponential and sine and cosine, then roots will not work because it looks like it only works with polynomial. Okay, so fsolve is more generic than roots. Okay, let's run this. And it had no problem running it. Earlier it had given me error. This time, because there are two functions, it works fine. Okay, now let's modify this function to suit our purposes. So we define this to be x squared minus x minus 2. And in this case, there's only one initial guess. Okay, let's just randomly choose minus 6. So if you see, it gave minus 1 as one of the roots, and that root is actually this one, which is good. If you want to find the other root, you need to give a different guess. So let's try minus 3 and see if you get that root. Okay, so again it gave minus 1. So there is this thing which is the root, the initial guess I chose, which was minus 6, is close to minus 1, and that's why it converges to the closest root. Since I chose minus 3, which is again close to minus 1, I again get the same answer. If you want to find the other root, you might have to give a guess which is closer to that one. So closer to 2. So let's give 5. Okay, so now it converts to 2, and that's the other root. Okay, so you can see that fsolve really depends on the initial guess you give. If you give a guess which is far away, sometimes it will not converge, and sometimes it will converge to the root which you just saw. So for example, let me choose, let's say 100 and see if it actually works. Okay, so here it worked. So this is a nice quadratic function, which is, it is convex. And so it actually gives you the root, no matter how far you are from the from the root. But there are functions where if you give the guess too far away from the root, then it will not actually converge. So you'll have to do some playing around. But since it's a numerical tool, you can actually do exhaustive search where you are actually trying different initial guesses so that you can get the solution closest to the root. So hopefully that was a good enough introduction to fsolve. We'll be using fsolve quite a bit in this course. And uh, the, the next time we'll be using, which is in a few minutes, would be to solve the inverse kinematics problem. But before that, let's do some videos. Any questions so far on okay, so I have a question here, which is if you give two guesses, would it give you two roots? We can try. Most likely, it just depends on how you define f. Let's give minus 6 and plus 6, right? And see what it gives. Okay, so it says it doesn't work, and that's because the way I wrote x square minus x, this can only take in one scalar value. If I wanted to take an array, then I need to put a dot here. That just does component-wise multiplications. Let's try this. I think it'll work. Yeah, so here's a way you can get two roots. Now, there are some assumptions here. I know that there are two roots, and that's why I put two inputs, right? If you knew there were 100 roots or 50 roots, you can do that, but you can also do something like this: 4, 5, 6, 3, and then run this, and then it will give you, well, in this case, give you minus 1, 2, 2, and so on, which means that there are just two roots. No matter what initial guess you give, it converges at. So yeah, you can use this to find multiple roots in this fashion. The same manipulator, and then we will talk about inverse kinematics. So here is the base frame. link 1. Let's call that px1 y1, and then the second link x2 y2, and that's q. So the link lengths are L1, L2, and the angles are theta 1, theta 2. If you like, you can call, and this is theta 1. Okay, so the inverse kinematics problem is given L1, L2, and xq equals x ref. Okay, so this is, you're given the x position of point q, and you're given the y position of q, and both of them are in the base frame. Okay, find theta 1 and theta 2. Okay, so this is very relevant in robotics because most times you are interested in finding how to place your hand or your robot hand at a certain position. So if you're specified the final end position of the hand, you need to find what angles the elbow and the shoulder needs to be at, and that's what the inverse kinematics problem is. Let's try to write the formula for xq and yq. So xq0, and this is from my forward kinematics derivation earlier. It's L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, and then yq0 equals L1 sine theta 1 plus L2 sine theta 1 plus theta 2. So this is given. Okay, yref is given, L1, L2 is given. We need to find theta 1, theta 2, and so on. Okay, so this problem is in a way root finding problem, because the way we can write this is essentially, so we can cast this as a root finding problem in the following way. L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 minus x ref equals 0, and L1 sine theta 1 plus L2 sine theta 1 plus theta 2 minus y ref equals 0. So if you like to call this as f1 is this, f2 is this, then fsolve basically has to be some function, some initial guess, theta 1, theta 2, and then that will give you your answer, which is theta. So this sort of, I'll write the code in a bit, but this is how you'll execute it. This function here would be f1, calling f1, f2. So once you set this up, you're essentially solving for theta 1, theta 2, given the lens and the x ref and y ref. Okay, so I'm almost out of time. Next class, I will show you how to set up this problem based on our earlier code of using fsolve. And once we do that for one point, then I'll show you how you can actually draw a curve, a circle, or more fancy ellipse, or whatever you want, by using the same idea, but to find theta 1 and theta 2 as a function of time. Okay, so angles of a two-link manipulator such that the end effector, which is q, is at a particular position. So here I have the manipulator, the position of the end effector or point Q is given here. This is something we derived in previous class. And so here we're interested in positioning the end effector at a certain point x ref, y ref, where x ref and y ref is something which you specify. And I would like to solve for theta 1 and theta 2, which does that. So again, this is an application of fsolve where we try to write a function f1 which will return f1 and f2, where f1 and f2 is the position of the end effector, this term, minus the x ref y ref. So here is a possible problem which we'll solve in Matlab in just a bit. Let's say this is our coordinate frame. The manipulator origin is here. And we want to place the manipulator at this point. So let's call that's x ref, y ref. We can pick a value for this. So let's say 0.5 and 0. Okay. So you can now start imagining how you would place the links, the two links, such that this manipulator would end up such that the position of the point Q is at x ref, y ref. So here is one possible configuration. Right? And the angles are here, this is theta 1, which is the angle made with the x-axis, x0 axis. And then theta 2 is going to be this angle. Okay, so this shows us what theta 1, theta 2 are more or less, but doesn't quite give us the value. Note that this is 1 meter and 1 meter. So this makes sense. This configuration makes sense. So we'll see how to use Matlab to solve for theta 1 and theta 2 using fsolve. Okay, and what I'm going to try to do is again try to code in front of you. I'm going to reuse the code which I wrote down for solving for the roots of the quadratic equation, and also in the previous class I talked about forward kinematics where I drew the manipulator. I'm going to use that code too. So you'll see how I put two codes together to solve for this inverse kinematics problem. First thing I do is open Matlab. I've opened the files which I wrote down earlier in the last class. So example roots was the file I wrote which solved for the roots of the quadratic equation. And then it gave me one of the solutions, -1, which is right here. And the other file which I wrote down last class was for the forward kinematics, which basically plots the manipulator for given theta 1 and theta 2. Okay, so now I'm going to reuse this code to write a code which does inverse kinematics. So let's start a new file. Let's copy paste a few things from here. You can essentially take this whole code, copy paste it here. Let's call this lecture 5 manipulator inverse, and then run it, and it will basically generate the code which does example root. So I'm going to try to modify this to get it to do the inverse kinematics of the manipulator. So first of all, I want this function to return the end effector position, okay, which is the position of point Q. And so the position of point Q is right here in my forward kinematics. So I'm going to copy that and paste it here. Okay. Now, in here, I want, so you can see that the good thing on Matlab is that it highlights things which are unused. So if you hover your cursor on F, which is, you can see a red line there, it says that the function return value f may be unset. That is, it is not really returning anything called f, and I need to write that here. Let me just change the font size so it's a little bit bigger than what it is shown here. Let me, so preferences, fonts, okay, better. Okay, so what I want it to return is f, which is now going to be x cube minus x ref. I'm going to define x ref, but let me just write it down that way, minus y ref. Okay, so now I have set x cube, y cube, and f, and that's why you don't see these red lines here. However, I still need to define all these values. Now, x is basically the input or the things which which the optimizer or fsolve can vary to find the roots. In this case, x is going to be the values for theta 1 and theta 2. So if theta 1 is my first argument, which of course I have to pass it over here, and theta 2 is my second argument, then this will work out to find cosine and sine, but still I need to find L1, L2. So there are many ways to define L1 in this code. One way is to actually define it here. Okay, L1, 1, L2, 1. Okay, let's just do it this way, and then I'll show you another way to do it. So this seems to be the simplest one. Okay, so I've written this function, which basically gives me the end effector position given, well, I've still not defined this. Let's define that also. X ref equals 0.5, y ref equals 0. Okay, so everything here is defined. All I need to do is give it an initial guess. So let's call that x0 for my initial guess. And since x0 has two things in it, it has theta 1, the first argument, and theta 2, the second argument. Let me just randomly assign it to be, let's say, 0.1 and 0.1. Okay, you can change that to whatever you want. Okay. I do not need this, nor do I need this. Okay, the first thing to do is to write the bare minimum code so that you can get it to basically run. So let's see if this runs. Okay, so it gave me two answers, minus 1.3181 and 2.362. Now, how do I check this? Well, one way to check this is to see if actually gives you x ref, y ref equals 0.5 and 0 when you sub that in this equation. So what we can do now is we can visualize this, and that might be the best way to see if this makes sense. So this is where I'll peek through the code I wrote for the forward kinematics, which basically gives me the manipulator diagram or animation given the angles theta 1 and theta 2. So all I need to do is copy the right code from my forward kinematics, which is right here. So here, essentially copy this. Paste it here. And note that I need to now take in the values which fsolve gave for theta 1 and theta 2. So these values are no longer true. So that will be x1 and x2. So everything else looks fine. So let's just run this. Okay, so what you see in the plot is the position of the end effector, which is the green, is actually 0.5 for x and 0 for y. So there was a question on chat. Let me see. Could you share these codes on Blackboard? I think I've shared these codes on Blackboard. Are other people able to access this code on Blackboard?
Yes.
Okay, so they are on Blackboard. If you look at in Blackboard, you will see a video. Just on top of the video, you'll see the lecture PDF, and you'll see the code right below it. Should be one file. So each block there is a unit consisting of the PDF, the code, and sometimes it might be a zip file and the video. So if you still have a hard time getting it, let me know. Okay, so this looks good. But you note that in my notes, when I showed you, I had a different configuration for the manipulator. It was actually not uh, V, like a V, but it was more like a inverted V. So how did I get that? Well, in this case, looks like there are more than one solution for this. In fact, you can get the other solution if you change this. So let's just change this to, I'm going to make a guess, zero point 0.5, zero point 0.5, or it doesn't have to be the same. Okay, it still gives me that. Uh, let's try 1 and 0. Okay, so here is the second solution to the same problem. So in this case, there are two solutions to the inverse kinematics problem, just like we had two solutions for x square minus x minus 2. And the only way you can get it is to, first you need to uh, uh, essentially try a number of initial guesses to see if you get multiple solutions. Now here are a few things. So once I get the code, I want to clean it up. And the reason I want to clean things up is because I noticed that I define length here, xref, yref here, and then the length is defined again over here. And sometimes, if you're trying to do some things like you suddenly decide that you want to change the length of the manipulator to try a different problem, and then you run this, then you're going to get something which looks like this. That's because you have defined lengths in two different places. So it's always a good idea to define all your uh, constant parameters in one part of the code and then pass them as functions instead of writing it in multiple places. So that's a good programming practice. So let me write this right here, and then let me delete this, of course, or comment it out. I don't want it here. And then this part also should be over here. So modifying the constants is just a matter of writing few different things in the first part of the code instead of trying to dig into functions. Now, once we have this, let me put all these things in a function called param, L1, L2, xref, yref, okay? And then pass this function as a part of my fun. And the way you do this is, so param, now this param goes in as second argument of my fun. And what I need to do now is L1, I know is, I'm going to copy this part, paste it here, comment it out. That way I know what I'm doing here. L1 equals param1, the first element, L2 equals param2, xref equals param3, and yref equals parameter. Okay. So if everything looks right, then Matlab will not have those yellow marks. So when you saw there was a yellow mark here, it went away. There was no red lines below everything looks good, then there would be none of these things. There's a yellow sign here. That's just because I did not put a semicolon. In fact, if you hover your arrow there, you'll say, tells you, you can terminate the statement with semicolon. Here, in case I don't want to suppress the output, I want to actually see it. Okay, so there was a question, why did we create myfun? The reason why we create myfun is because the way fsolve works, fsolve here, is that it needs to call a function which it can keep calling again and again to iterate over theta1 and theta values till it finds the right value. So uh, usually the reason why we write a function is because that code can be called by another function again and again. If you remember the first lecture, we had this code where we were trying to find the sum, and we were trying to use that code again and again to find sum of different arrays. And the best way to do it is to write a function which is called repeatedly by the same part by different arrays in the main file. So that's why we write my function. Okay. And let's run this. And so now it's all packed together in one place, the parameters, as well as we got the final output as desired. Okay, so that is how to solve inverse kinematics. Now let's take it a little bit a level up, which is, can we use this manipulator or the end effector? Okay, so example for tooling manipulator is your hand, as I said, if you want your hand to draw, let's say, a circle, okay, then how do you solve the inverse kinematics problem? Essentially, it is solving the inverse kinematics problem again and again, given different points. Okay, so let me switch gears to my tablet, and then I'll show you the code. I will not write that code in that case. So how do you extend this to draw a curve instead of just pointing to a location? Okay, so let's say that we want to draw a circle. So I'm going to draw the axis, and then my circle is centered at 1 comma 0.5. So if this is some the axis, then 0.25, 0.5, 0.751, 0.25, 0.5, 0.751. So my center is at 1 comma 0.5, so it's about here. And then the circle is of radius 0.5. So it will somewhat like this. Draw it with a different color. So something like this. The center is 1 comma 0.5. So the trick behind extending the code, which I wrote down for a point, is to essentially make points along the circumference of the circle, right? So equidistant points. And then tell the manipulator to basically go from one point to another point and so on. So the xref in this case will be the center plus 0.5 cosine of, let me call that phi, okay? And this is basically the parametric equation for circle. It basically is the center of the circle plus radius times cosine phi. Similarly, yref is 0.5 plus 0.5 sine of phi, where phi goes from 0 to 2 pi. So this is known as the parametric equation of a circle, which is x equals x center plus r cosine phi, and y equals y center plus r sine phi. Okay, so with that, let me show you the code which I'm sorry, I was muted. Okay, let me restart. So I basically wrote this code offline, and I'm going to show you how this code is a modification of the forward for the inverse kinematics code for a point. Essentially, I extend my xref, yref to be points on the circumference of the circle. So xref, yref. I have an initial guess, theta 1, theta 2, and it's going to be the same for each and every point. So this is not the only way you can do it. You can do multiple guesses for multiple points. In this case, it just works. I have an array which has all zeros. Then I populate this array with the values which come from solving fsolve. So each time I solve fsolve, I get an x. That x is the solution at that particular reference position. I save that in theta 1 all, and I keep doing that for different points. So here is the rest of the code. It's pretty much the same one, except there is a for loop, which takes care of the fact that I don't have one single point, but multiple points. Okay, so let's say running this will give you the circle. Okay, now there is explicitly the time really doesn't appear. There's no dynamics in the manipulator, and that's something which we'll do in a future class. But for now, for most of the times, if you're doing something very slow with a manipulator, then you don't need to care about the dynamics of the motion. So this is purely kinematics. Okay, are there any questions about this or anything we talked so far? Okay, what happens when x ref equals 0.05, y equals, okay, so this is for the pointing example. Let me try that. X ref 0.05, y ref 0.05. Okay, any guesses what will happen? I think it may not give the solution because that's so close to the origin. You can try that. It actually gave me a solution. There it is. Figure. Here it is. I mean, there are possible places where there will be no solution, and I can give you some examples. So you know that the reach of the manipulator is 2 meters, right? 1 meter, 1 meter. So anything beyond 2 meters, it will have a hard time doing. So let's just try to put, let's say, 2.1 and 0.1. Okay, so this we know it will not be able to solve. Let's try that. Okay, so though it did that, you can see this, it says no solution found. So it's actually very important to check if this converged or not. Just because you got some answer doesn't mean it's the right answer. So this is something which will come in the homework, but fsolve has more fsolve. So fsolve has some more arguments, output arguments, which I did not quite discuss here. So these arguments are fval and exit flag. And I recommend that when you write solve, use fsolve, you always call the other two arguments, and I'll show you what happens when you call them. Okay, so we'll make it plot show x, fval, and exit flag, and run this. Okay, so let's look at x. X is the solution. Fval is basically telling you what is my function, what is this f. Okay, this is the value of the function, and for it to be find the solution perfectly, what needs to happen is that f should be 0. So in this case, you see that f is not 0. Okay, no wonder the exit flag was not 1. So exit flag basically tells you if the solution converged or not. So if you look at documentation for fsolve, here is the exit flag value. So if it is 1, it means fsolve converged to a root. 2, 3, 4. The one which you got is -2, which is it's not converged to a root. So that's always a good idea to check if it converged or not. Let's go back to 0.5 and 0 and see if it actually converged or not. Okay, you can see that the solution is here. Fval is negative e raised to 1 e raised to -9. So that's very well close to 0. And then the exit flag is 1, which means it's converged. Okay, so always check for the exit flag. Okay, any other questions? Okay, no questions. Okay, so next thing we'll be doing is